Okay, so we just finished talking about slope fields or direction fields for differential equations. And now we're going to move on to a way of kind of approximating solutions to differential equations. So normally, if you're given a DE, say of this form, y prime equals f of xy, and some initial condition, y of x naught equals y naught, the ideal situation is that you could find an exact solution to this. You could find a function y which you could describe in complete terms that gives me the solution for this thing. If we are able to do that, then we call that taking an analytic approach to solving that DE. And it's great. That's kind of a best case scenario. But if you study differential equations, you're going to find that there are a lot of differential equations that arise in the sciences and elsewhere that are very, very difficult to take the analytic approach on, and in some cases even impossible in a certain sense. So we tend to want to have other options available to us if we need information about the solution to a DE, even if we can't get all the information. So one way of doing that is what we did in the previous video, taking a qualitative approach. Which is trying to extract information out of this differential equation without needing a full solution for it. And those direction fields were one way of doing that. A different way of trying to extract information out of this is what's called a numerical approach. And a numerical approach is an attempt to get approximations for our solution. And we're not getting an approximation for the entire solution, but we want approximations for specific points on the solution curve. That's kind of the idea. So there's a number of different methods for doing this. In fact, if you go on and study this stuff and do like a graduate program in it, there's entire graduate level courses that only deal with numerical approaches to differential equations. There's lots and lots to talk about here, but we're only dealing with one method. This is what's called Euler's method. And here's kind of the basic idea. So again, we're assuming that we don't have a solution to this differential equation up here, but because it's in that form where I have y prime equals a function of x and y, I am able to find slopes of points on a solution curve using this. So from that, we can do something that we did all the way back in Calculus 1, which is called a linearization. We can basically find the equation of a tangent line if we know the slope of that tangent line, which is what this is useful for, and a point on that tangent line, which our initial condition will help us with. So let's suppose that we have our initial condition. We know that the point x naught, y naught is on our function, or is on our solution curve. We want to find the tangent line there. I can plug x naught and y naught into this function to get the slope of that tangent line, and the equation for it would then be this. L of x, which again, L for linearization, equals y naught plus f of x naught, y naught. Remember, this would be the slope of that tangent line times x minus x naught. Okay, so this is something you talk about in Calculus 1. What this will do is if we move a short distance along that tangent line, then we're going to expect whatever point we land on that tangent line to be relatively close to the corresponding point on the solution curve. So this will give you a better idea of what we're talking about. Let's suppose that this blue curve here is the solution curve, but we have no way of actually finding the graph of that thing since we are assuming that we can't find the actual solution to our DE. But we have enough information to sketch this red line. So here's x naught, y naught. That's my initial condition. That's where I got that point from. We compute our linearization, which is this red tangent line, and then we select something called a step size. So step size is this value h, and what it means is how far do I want to move from my initial x value, x naught, to get to my next x value, x1. So we imagine h usually as being a fairly small number, since these approximations only really work very well as long as we stick close to x naught here. But I select this step size h, and I add it to x naught to get to x1. and then I plug x naught plus h into the equation for my linearization to get the corresponding y value, y1. So what would that look like? Well, y1 is equal to L of x naught plus h. Remember, L is my linearization, which is equal to y naught plus f of x naught y naught. And then x naught plus h from here gets plugged in for the x that would have been here. But notice now I have x naught plus h minus x naught. So these x naughts cancel, leaving me with just the h. And now I have this. y1 is equal to y naught plus h f of x naught y naught. Okay? So what this does is it gives me an approximation for this little point. However, that's as nice as that is, it may be desirable to get an approximation for a point that's further along this solution curve. We may not want to stay that close to x naught. So what we can do is repeat this process. Sorry, my dog is snoring behind me. So how do we repeat that process? Well, now what we're going to do is use our new point, x1, y1, as kind of our new starting point. So what we're going to do now is we're going to compute what the slope of the tangent line to this solution curve would be for this value x1. So you can see that if I were to sketch a tangent line there, it would look something like this. But then we're going to take that little piece of that tangent line and basically copy and paste it down here. So it does something like that. Okay. Now I have another picture down below that's going to do a better job at showing that. But that gives us kind of another piece or another little line segment that we can use to approximate the next point, whatever we would get by adding our step size to x1. So that's going to result in basically the exact same equation, but my x naught, y naught here is going to become x1, y1, since we're thinking of that as our new starting point. My x naught, my y naught here would also become a y1, and then the result of that would be y2. So what we call this is an iterative method. Basically what it means is you have this formula, and we are going to get outputs from it using some starting point. But then those outputs are going to be fed back into that same formula as inputs. Produces a new output that gets fed back into here, and then it kind of just cycles like this for however long we want to do that. Okay, so here's the general formula that, summarizes all of this. So if we want to repeat this process to approximate y of n plus 1, if we already found yn, it's equal to yn plus h of f, or h times f of xn yn. Okay, and here's where we can think of xn as x naught after adding n step sizes to it. Here's what this looks like when you go through this iterative method a few times. So here in red, I have a solution curve, and I have my first Euler approximation. So basically that initial tangent line. Here's what it would look like if I use a step size of 0.5. And I'm trying to go from x equals 0 to x equals 1. So I'm working my way from 0 to 1 using intervals of 0.5. So 1, 2 jumps in total. Euler's method is going to give me a tangent line that gets to the end of that first step size, and then it's going to recompute my tangent line and give me a new one that I sort of like imagine gluing on to the end of that old one. So now I'm getting these two line segments. The y-coordinate of this point is going to be used as an approximation to the y-coordinate of that point. If I increase my step size, let's say I increase it to 0.25, now I'm making adjustments more frequently. So if you want to think of this purple line segment as an adjustment to our approximation, then decreasing my step size will give me more adjustments sooner in the process. So there's 4 intervals of size 0.25 between 0 and 1, and you're going to see these adjustments so that this sequence of line segments more closely hugs the actual solution curve. And I can see that the y-coordinate of that point is closer to the actual y-coordinate of my solution curve in this case. So small error there, slightly larger error there. So the kind of the moral of that story is that if you want better approximations from Euler's method, you have to choose smaller step sizes. Okay? All right, so here is our example that we're going to do where we're going to work out a numerical solution or a numerical approximation for a differential equation. So here I have y prime equals x squared plus y squared. So this thing right here, the x squared plus y squared, is what we're thinking of as f of xy. It's equal to x squared plus y squared. Euler's method says that y of n plus 1 is equal to yn plus h times f of xn yn, okay? Where h is my step size. In this problem, what are we using these for? It says that we want to use Euler's method to approximate y of 0.5 given this differential equation, and notice where our initial condition is. It starts at 0, y of 0 equals 1. Then we want to use a step size of h equals 0.1 for this approximation. So y naught is the same thing as y of 0, and we know what that is exactly. It's given to us in the problem. It's y of 0 equals 1. So I can put a 1 there without having to do anything with Euler's method. But now Euler's method says that I need to take this y1 and this x1 and feed them into this iterative formula right here. So in order to get y1, I have to plug y naught plus h f of x naught y naught, which in this case would look like 1. That's what we said that y naught was equal to, plus h, which is 0.1, times f of x naught y naught. Well, x naught, again, is 0, y naught is 1, and f is x squared plus y squared. So I have 0 squared plus 1 squared. This is equal to 1.1. Okay, that's what I would get when I plug y naught into that formula. Now I have a new output which gets fed back into this iterative formula to get y2. So now y2 is equal to y1 plus h times f of x1 y1, where y1 was 1.1, h is 0.1, f of, what is x1? Well, remember, to get these different values of x, we keep adding our step size over and over again to our original value of x. We started at 0, and now we're adding a step size of 0.1. So that would just be 0.1 squared plus 1.1 squared. I shouldn't really have the f there. That should just be 0.1 times that. Okay, as before, you put that into a calculator. This time I'm going to get an approximation, approximately 1.22. Okay, and then this process repeats. So I would take 1.22, feed it back into that formula, see what pops out. The other values in this table I'm just going to write in because at this point it's just repetitive to do all of this over and over again. 1.57, 1.84 is where we land. So I've used my step size to count my x values up to 0.5, and I got y5 is approximately 1.84, which is what y of 0.5 is. Okay, this would be my solution. Now, it's not an accurate solution. We know that it's an approximation, but what this means is that whatever the solution to this differential equation is, when I plug 0.5 into that solution, I should get a number approximately equal to 1.84. Okay, so that's going to wrap up 9.2.